knots and to a certain extent links. So I want to go back and talk about associated to a knot inside. This is how you get time over the one-dimensional topologist. Is I can't actually draw knots on command. So associated to a knot inside S3 or a link that might have several components, we'd like to understand something about the knot, and so we'd like to associate it to some piece of information that's invariant. So the first thing you can do is you can just take your space and you can throw the knot out, and that's a complete invariant of the knot. But ideally, what we'd like to do is we'd like to strip out some information from this that's a little bit more kind of concrete in nature, and in particular, do it in a way that's invariant under kind of deforming the knot. And so, because homotopy theory is invariant under deformations, the first thing that you can do is you can look at the fundamental group of S3 minus K. It's not interesting to do that for the knot itself because every knot and every link is either a circle or a whole bunch of circles. And there's a kind of concrete method for calculating the fundamental group of a knot. So when we do this, one way that we can make our lives a little bit easier because we hate base points is we can, instead of drawing one base point in the picture, we can kind of imagine that we've got a little diagram sitting inside the plane and living over top of it, or near the plane, and living over top of it is some kind of big contractible space that we're looking down from. And if we do things in those terms, then what we can do is we can, instead of specifying a loop, what we can do is we can imagine that we can draw paths that drop down, circle under things, and come back up. And each of those specifies uniquely an element in the fundamental group. And so that means that in my picture of a knot or link, I can specify a element of the fundamental group by kind of drawing a little edge here that goes underneath, or some composite of those, because then that kind of implicitly drops down, goes underneath, and comes back up. And so if I do this, and I draw an orientation for all of my edges, that lets me specify some certain particular elements inside the fundamental group. And so, for example, for every edge that appears in this picture, I can have a loop that kind of hooks around underneath it using the right-hand rule, like so. And so I can give that, both of those, some name, A, and it represents an element in pi1. And we get some relations between those. So for example, if I have an edge going upwards like this, and I've got two more edges, B and C, let's say they're oriented this way, and I want to understand the relationship between those. I can, for example, draw the edge associated to C that goes around by the right-hand rule. And that's homotopic to a path that starts here, goes around underneath, and comes back up this way, which under the standard but not always ideal rules for composition in the fundamental group, this says that C is the same then applying B, then applying A inverse. Or, said another way, it says that, did I get that right? I got that right. This says that B is equal to C to the A if I use exponential notation for conjugation in the fundamental group. So every time I have a crossing, I get a relation that looks like this. And so we can imagine that we've got some kind of highway, and if we go underneath it, it turns B into its conjugate on the right, like so. And so the theorem about this is converting representation. And the fundamental group of this knot complement has a presentation with one generator per part and one relation of exactly this type per crossing. And we kind of do our best to keep those carefully separated from each other so that we never get our orientation wrong. So this is kind of a weird presentation for a group. And one of the reasons that it's weird is that it doesn't really use the whole power of the group. All it really uses is the conjugation operation in the group instead. So this only depends on conjugation and not the full power of multiplication. And so that leads one to ask, is there kind of a weaker piece of structure that one could impose on this that doesn't have the whole multiplication of the fundamental group, but where we still get a Bertinger presentation and we get a new type of algebraic object. And that algebraic type of object is going to be called a quandle. But to motivate the definition of a quandle, we'll say it's a set Q with a binary operation that's written as A comma B maps to A to the B, like this, or sometimes written as A with a little diamond. I've got the diamond pointed in the wrong direction, like so. And I want it to satisfy a couple of rules. But the rules that I want it to satisfy are both rules that are going to be from analogy with the conjugation rule and the fundamental group, but they're also going to be things that are going to explicitly make this quandle structure into a non-invariant when we write down a Bertinger presentation. So there are famously 3 Reidemeister moves. So a Reidemeister move is a certain type of move that you can do on a small portion of the knot diagram to turn it into another knot diagram without changing the underlying type of the knot, or in a link diagram to not change the underlying type of the link. So one Reidemeister move says that I can interchange a small twist with not having a twist at all. Another Reidemeister move says that I can interchange a small underpass like this with having 2 parallel elements. And the third Reidemeister move says that if I have 2 crossing things and something that goes underneath them, I can pull that crossing underneath, or I can pull that crossing across so that it looks like this. And there are various versions of these depending on the way I orient my arrow of that as well. But this is good enough for now. All right, so what does this say? Under my conjugation rules, if I say that this edge is A, then as I come through here, this edge on the other side is related to A, and maybe I should have drawn that the other direction so that I could write my conjugation a little more nicely. If this is A, then as I come through, I've got the edge A going underneath A, and so it turns into A to the A. And so I want that to be basically the same as A itself, which basically means that I need the identity A to the A is equal to A, which is a perfectly good thing that happens for conjugation in a group and it commutes with itself. So if you conjugate G by G, you get G. This one here, if I start with an element, I drew this one backwards. That's great. If I start with this element here and I write this is A and this is B, first B comes across and turns into B to the A. This one here, C, if it comes across, and you believe me about my getting my orientations correct, this turns into C to the A. This says that, well, if I want these to be the same, I want it to be essentially the same as if I started with only 2 distinct elements instead. So I want this identity to be the same as saying that C is equal to B. So that's my second relation. It's basically that A is, reversible. And the third rule is a little bit more strange. This is A, and this is B. This is A, and this is B. And I name this element D. First, D comes across and turns into D to the B. This element here, by moving B under A, so this is B to the A. And so this element on the right is D to the B to the B to the A. Whereas this is D, D to the B, and then D to the B to the A. So I have a third relation that says D to the B to the A is equal to D to the B to the B to the A, which you write it down in terms of group conjugation, it looks a lot better. It says that A inverse B inverse DBA is the same as B inverse DB conjugated by B inverse AB. And all the B's cancel, and you do actually get an identity for the group conjugation. So those are the three rules for a quandle. It satisfies, first of all, A to the A is equal to A. Secondly, for all A, B to the A is in bijection on this quandle. And thirdly, that we have this pseudo associativity rule. D to the B to the A is D to the A to the B to the A. So those are the identities that a quandle is supposed to satisfy. And so, the principal example of this is a group. A group as a quandle structure. Namely, I define A to the B to be equal to literal conjugation. But you can also get smaller quandles by taking a group and throwing stuff out. Namely, any subset that is closed under conjugation is also closed under the conjugation operation. So any subset of a group is closed under conjugation. Is also a quandle, a subquandle. So as an example, what I can do is I can take the symmetric group on 3 letters, and I can look inside that at the subset consisting of just the transpositions. So that's a subset, and it's closed under conjugacy. That means it's a subquandle. And if you like, it's got a multiplication table, where if I name these 3 elements A, B, and C, how does the conjugation operation go? Well, everything conjugates itself to itself, and everything conjugated by not itself turns into something else that's not itself, like so. And well, probably an easier way to remember this is to say A to the B is X to the Y is equal to Z, if and only if X equals Y equals Z, or all 3 are distinct. So this is a very specific quandle that lives inside the symmetric group on 3 layers. All right. So a proposition that's basically boils down to this Reidemeister move verification that we put in by definition, is that every link in S3 has an associated quandle. With a working representation. Now, to actually say this, I need to know what it means to take a set and produce like the free quandle on that set, or take some relations in a quandle and construct the quotient quandle That's all falls into the realm of stuff you can do whenever I write down any random set of rules in algebra I'm allowed to follow.
So is the quandle the set of loops that start at your contractible space at infinity and go around one of the arcs?
So the quandle is not 100% quite that, but I'll talk in a little bit about exactly what the quandle is in terms of the geometry. Right now, I'm just writing down some generators and relations for a particular presentation, and I get a quandle, and I don't know that I have any geometric content. All right. Yes.
So you gave the work in your presentation as a presentation of pi1 of S3 minus the complement space, right?
Yes.
So is this just an instantiation of that example that every group is a quandle structure and we're just kind of forgetting it's a group?
In fact, no. So what happens here is that there is, so this kind of forgetful thing where I can take a group and forget the group multiplication and just remember the conjugation and get a quandle. That's actually part of a pairing. Over here I have quandles, and there I have groups. So there's a forgetful functor that goes from groups to quandles. That functor has what's called a left adjoint. I can take a quandle and I can make a group out of it by enforcing. If I've got a quandle, then I get a generator for every element of my quandle. And every time I've got a conjugation relation, I turn it into a literal conjugation relation in the group. And so the assertion is that I don't actually know great notation for this. So let's just say, what's the Greek equivalent of Q? Or
It's kappa.
Kappa. Great. Let's say Q1, the fundamental quandle of a knot. And if I take this, and I apply this free instantiation of a group, what I get is something isomorphic to pi3 of the knot complement. So the group I get isn't exactly the quandle, but it's the simplest possible group I can build based on the quandle operations.
If you have, can you have different links with the same quandle?
You can't,
Different fundamental group?
in fact, I think, I'm not sure if I heard you correctly, but I think you might actually have the opposite case. So there's a theorem. And this theorem is due to Joyce, who kind of introduced these. So there exist knots, or sorry, how do I say? The quandle is a kind of complete knot invariant. Mod reflection. It doesn't detect tangents, but the fundamental group of the knot complement is not. So you can have two knots that have the same fundamental group of the knot complement, but different quandles. And one of the ways that that happens is that in this adjunction, the group you produce has some special conjugacy classes in it, some things that were actually in the image of the elements of the quandle, and so you've got some distinguished elements inside the fundamental group on the other side. So unfortunately, just like with groups, writing down a presentation feels great, but it can be very difficult to take two presentations and say, hey, are these presentations actually presentations of the same thing? Or is this a presentation of something trivial? And so what we do in those types of cases is we study invariance. So at this point, if I was going to be teaching a basic class on this, I would give a definition of what a quandle homomorphism is. But it is what you think it does. It's a map between quandles that takes the operation to the operation. So as an example, If I've got a knot complement or a link complement, a homomorphism from the fundamental quandle of a knot over to this quandle that lives inside the symmetric group on 3 letters, what is that supposed to be? Well, it's going to take every generator and associate to it one of these 3 elements in this set. And that assignment has to happen in a way so that whenever I have a crossing, I get a relation. The 3 elements involved in that relation either all have to go to the same element or they all have to go to distinct elements. This is basically the same thing as the so-called tricoloring. It takes the arcs in your knot diagram and assigns a color from this 3-element set to each of those arcs in such a way that at each crossing, you either have 3 distinct colors or 3 of the same colors. So you can study the knot complement a little more rigidly by looking at some specific quandles and looking at homomorphisms out of them. And so, for example, you could come up with tons and tons of weird generalizations of what a tricoloring is by writing down a bunch of random quandles on the right-hand side by, I don't know, going out and playing in the symmetric groups. There are tons of things in the symmetric groups. Okay.
Is this the same thing as a simply branched double cover complement of the knot?
Is this the same as a simply branched double cover of the complement of the knot? I do not know off the top of my head. I would have to think about that. It sounds kind of like it.
I mean, I guess you apply enveloping groups and get that from pylon to the symmetric group.
Yeah. Yeah, right. But it's a very, whose isotropy all lives inside certain things. So, but the branching happens associated to those certain generators. So, okay. I don't know. There's probably some relation, and I should shut up because I don't know what I'm talking about. I have questions.
Is the 3 colors specialty?
Sorry, say again?
Arming 3 elements on the right, is this necessary, or you can do any general?
So it's not necessary to do 3 elements on the right. This is just kind of the smallest interesting quandle that there is out there. So I could do something inside the symmetric group on 4 letters. So, that's got like 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. So that's like a 6-element set. And then I could say, well, what are the rules for this? Well, I've got 6 colors, and well, okay. You can fool around with some description of what the quandle operation is doing there. That this quandle is some kind of goofy double cover of this 3-element tricoloring, and so this is some kind of enhancement of what the notion of a tricoloring is. And there are more, but Let's talk about the geometry of the situation. So ideally, when I write down some abstract algebraic gadget associated to a knot complement, maybe there's some piece of geometry that goes along with it. And so I want to talk at least briefly about how we get that. So let's say we've got a knot or a link sitting inside R3. I want to know, how can we write down the elements of this kind of fundamental quandle associated to it? What's the operation attached to them? And the easiest way I know how to do that is to kind of take the knot and thicken it up a little bit. So what you do, this is really going to strain me, so give me a second to stop talking and draw like that. So we have this kind of thickened up pretzel, which is essentially some torus that sits inside S3. And that torus, if my knot, if I choose an orientation on it, then I get something special on this torus. Namely, I get a rotation around here according to the right-hand rule. Or at every point in the torus, I have a direction to rotate it around the core that's been cut out when I take the knot complement. And so this gives me a map from this torus, S1 cross S1, into the knot complement. And that means that one thing I can do is I can look at paths that start at a base point and end at the torus or vice versa. Definition. The kind of not quite fundamental quantile according to the original definition, I'm going to define this to be the relative fundamental group, pi 1 of S3 minus K, relative to this torus sitting inside. So by definition, this is homotopy classes of paths in S3 minus K that start at T2 and end at the base point. So. Where their endpoint is allowed to move around freely. So if I've got some path living inside there, I can make that homotopic to another path by one parameter deformation that's allowed to move the endpoint willy-nilly around inside the torus, so long as it stays inside the torus for the whole duration. And given two such paths, alpha and beta, I want to construct a path that I'm going to call alpha to the beta. And it's going to be built in the following way. It's going to involve some path concatenation. And it's also going to involve this circle action. Namely, I've got alpha as a path that starts at a point P and ends at the base point, and beta is a path that starts at the point Q and ends at the base point. And I've also got this kind of rotation that goes around the torus at this particular point Q. Then my element alpha to the beta is the path composite alpha concatenated with beta inverse, concatenated with, say, this loop around the knot, starting at the point Q and following the rotation around the torus, and then concatenated with beta. And hopefully, if I've gotten all my inverses and my directions correct, then this genuinely defines an operation that satisfies the conjugation type rules that we might expect. So let's check it out. So what happens if we do alpha to the alpha? That's alpha concatenated with alpha inverse, concatenated with the little loop at the base point P, concatenated with alpha. And that's equal to the little loop at the base point P, concatenated with alpha. What's that path doing? That path is starting at the point P, going around, and then following the path alpha. But that is homotopic to alpha because this end of the path is allowed to freely move around inside the torus. And so I can gradually shrink the amount of time it's spending and retract it down to just starting at the original base point of the path. So things genuinely conjugate themselves to themselves. All right. The second is alpha to the beta to the gamma is alpha to the gamma to the beta to the gamma. And I'm going to leave this as an exercise in conjugating stuff, because that's what it boils down to. All right, so in this sense, if we want a quandle, the natural structure that we need, that we got it from in this particular situation is quite general. So we can get a quandle by starting with 1 is space x, 2 is space 1. In this situation, we had an inclusion of the space x into the space y, but that's not 100% necessary. We can just start with a function f from x to y. Hopefully it's clear that I meant a continuous function when I said function. We need an S1 action on x, a continuous S1 action on it, and 5, a base point. If I put all those ingredients together, then this recipe gives me a quandle structure on the relative fundamentals of pi1 of y relative to x at its base point. And from a homotopy theoretic point of view, that's also the set of path components of the homotopy fiber of x to y. So we take x and its mapped to y and the base point of y, and we construct some homotopy pullback. Here, the set of path components of this is a one. The particular situation we started with, we had a knot or link diagram and the circle action on the torus that came from being in the little neighborhood of the knot. So I'd like to note, just kind of for the record, a parallel here. One of the parallel is when we talk about the fundamental group X, one of the ways that we can talk about the fundamental group is by looking at the loop space. What we can do is we can take the map from the base point to X and form this same kind of homotopy fiber. The space of paths in X that start and end at the base point. And that gives us a new space, the loop space. And pi naught of the loop space is a group. But the loop space is even cooler than that. It's not just something whose pi 0 is a group, but there's a very nice, mostly nice, there's a kind of nice multiplication on the loop space where I can take two loops and I can concatenate them. And that satisfies mostly associativity and mostly having inverses and mostly having an identity in a way that I would also go into great detail about if I was teaching Math 83 or 1 right now. I'm not. I'll just assume that we can do this. And there are kind of rigid versions. Or I could say, this is the kind of structure that I might see if I had a topological group. Is there a way to take a space and produce from it a topological group that's basically homotopy equivalent to the loop space? And there it is. And that falls into something that's called convolution. Or I can construct a topological group whose set of path components is telling me about the multiplication on the loop space, but in general encapsulates the whole structure. But that was our remembrance of what happened before in homotopy theory. So my assertion is that, in fact, this structure over here admits the same kind of rigidification in some sense. there is a way to take this setup where we've got x and S1 acts on x, and we've got y, and y has a base point, and we've got a function from x to y, and producing from that this fiber and rigidify it to a legitimate topological quandle. A topological space that has a binary operation on it that satisfies all of the rules that a quandle does, and which is homotopy equivalent to the thing we get by taking homotopy fibers.
Please tell me that you're going to call it a condyle.
A condyle? Oh. Is this what you're telling me?
Yeah.
50
Maybe-
points
maybe
for
Marcus
Gryffindor.
will like that.
Yeah, no. And the idea had not occurred to me. I do not have your talents. Are there any non-pun questions at this time? All right. Talk about abelian functions. Slash group homology. So there are a bunch of different perspectives on group homology and group cohomology. When I have a group G, I get a bunch of groups associated to it. The homology groups of G is coefficients and the integers, which kind of were originally defined as the homology groups of a classifying space, which I guess was originally defined as the homology groups of a KG1. But the kind of dissatisfaction with this process led to a definition that's purely in terms of algebra. And so one of the definitions in terms of algebra is to regard this module Z as being something that I could freely exchange. So there's a new definition that's algebraic that uses kind of the module variable. I view Z as a special type of abelian group with an action of G, and I compute X groups inside there. But there's another interpretation of group homology that's in terms of the group itself. And the way that goes is that the homology of G with coefficients in Z is gotten by saying, well, what is H1 of G? That's abelianization of G. And so what we could do is we could say, well, what is the homotopy theorist version of taking a group and making it into an abelian group? There's a so-called derived functor of abelianization. It's a non-abelian derived functor by contrast with the ones involving Ext and Torn. It's a derived functor in the sense of where we take a group and we resolve it by free groups, but we have to resolve it by something simplicial rather than just a chain complex. And this abelianization process, taking an object and turning it into kind of the best possible abelian group object that we can build out of it, turned out to be profitable in a number of other situations, like looking at rings or looking at commutative rings. Specifically work of Andre and Cohen. And so what I'd like to do is I'd like to talk about abelian quandles and what abelianization means for quandles. So an abelian quandle is a quandle Q with an abelian group structure. So it's got maps Q cross Q to Q and an inversion map and etc. And there it is. And abelian quandle is more specifically is equivalent data to an abelian group A with an invertible operation P that goes from A to itself. Specifically, an abelian quandle is going to be an abelian group with a quandle operation that I kind of have to write like this rather than A to the B to not get myself confused. And this operation can be explicitly expressed in terms of the operators. And so abelian quandles turn out to be the same as modules over Z adjoining T to the plus or minus 1. So as an example, if I take this fundamental quandle associated to a knot, and I take it's an abelian group, that gives me some kind of module over this ring, some kind of abelian group that is an operator, given by shifting by T. So we might ask, what is this group? And in fact, it turns out to be a known group coming from the geometry of the situation. Namely, if I got S3 minus a knot, I can look at its first homology group. That turns out to be isomorphic to Z by the Alexander duality here. And that means that there's a cyclic cover of S3 minus K by some space Y that's acted on by the abelian group Z of deck transformations. And the first homology group of Y is isomorphic to this abelianization of the fundamental quandle. This is the so-called Alexander module of the knot. And it provides some interesting information about what the knot is doing. So we might ask, question, can we strip out any more useful information? Namely, this here is an H1 group and it's an abelianization. I could ask, can I get more information by homotopy theoretically analyzing this type of setup in the same way that I got other group homology groups by taking a group and looking at the derived structures of abelianization? Yeah. The answer is yes. And this theorem is due to Zimmet. Yes, we get kind of quandle homology groups. And they agree with kind of groups that people have written down. with difficult chain complex calculations. So once upon a time, you might have thought about group homology entirely in terms of homogeneous or inhomogeneous chains or cochains, and written down chain complexes that calculated group homology in terms of those. But there's also the conceptual interpretation. The theorem is that these chain complexes that were written down to kind of match what the structure we saw on the group theory side looked like also gives us back these quandle homology groups that are defined in terms of derived functors of abelianization. Okay. But we are not satisfied by this entirely. We might ask, well, when I said more, I didn't just mean I wanted a whole bunch more groups. Maybe I'm a homotopy theorist and I said, look, I've got this situation where I've got this geometric space, I've got this topological quandle. I could ask, what are the cohomology theories? For quandles. What are all the possible ways that I could write down, take in a quandle, produce a sequence of abelian groups that satisfies, I don't know, all kinds of line exact sequences and fun stuff like I'm used to doing with group cohomology and with homology and cohomology of spaces. And the answer kind of comes in two parts. The first part gives an analysis of what free quandles look like. If X is a space, then we have the following theorem. The free topological quandle on X has the homotopy type of some certain very specific fiber. And that's from X cross S1 to X smashed with X cross S1, X plus smashed with S1. So I take a bunch of circles gotten by crossing with X, and I map it to a corresponding wedge of circles or index family of circles parameterized by the points of X. The fiber of that is the free quandle on X. And because generic topological quandles are built out of free quandles, that lets us completely analyze information about what cohomology theories could be by saying, what do they do to free quandles? And so, the theorem says that the so-called stable homotopy theory of quandles is a category of modules over a very specific ring spectrum, which is some kind of stabilization of what we get by applying this to a bunch of spheres. Category of modules over something that we take by getting the sphere spectrum and taking the group algebra with respect to the integers. And so, in particular, if M is a spectrum with action with an endomorphism, T, that is a weak equivalence, we can get from that homology of a quandle with coefficients in M and cohomology of a quandle with coefficients in M by taking some kind of derived abelianization or derived stabilization of the quandle and then smashing it with M, mapping out to M. over this ring. So integer homology is one particular example.
Do you want an automorphism to be? That is a weak equivalence.
Yeah, it's a weak equivalence. It's good enough.
I could look a little closer. Yeah.
Could actually be an automorphism. I can rigidify it to an automorphism, but I don't know. I gave up on making things actually true. No, it's good enough to have things mostly be true. All right, that's all I wanted to say. Thank you very much.
Question? Is it easy to say what the higher derived homologies of the quandle associated to a knot are?
Is it easy to say what those are? No. So one of the things that's really kind of weird about this is that there's a pet. So you can kind of embed quandles into pairs of spaces, where if I have a quandle, I can construct like a group in its classifying space, and then I can construct like some map that looks like this. And this is now an S1 space, and this is pointed, and vice versa. So there's a way to convert this quandle, which is a thing that has one operation, to a pair of spaces. And the pair of spaces is really nice to interpret, but the passage back and forth is really weird. And so when you calculate these derived functors, you get this weird kind of juggling thing where when I write down a resolution of this quandle, I'm simultaneously resolving BG, and also I'm resolving this S1 space on the other side. And so you get these weird kind of periodic patterns. It's kind of hard to compute. It's never finite dimensional. It goes all the way up unless you, for almost every non-complement. So that's strange. That's something I'd like to understand. Yes.
Does the category of quandles have like any nice properties? Like, I guess the motivation for my question is like, I want to understand slightly better, like what properties I should expect a cohomology theory for quandles to satisfy. Like, do quandles form an abelian category, or at least like an exact category?
No, they don't form any of that cool stuff. They are, no, they are a lot closer to a category like sets than they are to a category like abelian groups. The coproduct's terrible, in particular, which is my personal metric for like how sad I am about a category. Yeah, so as a result, doing these types of calculations, there's a big passage between the quandle and its associated abelianization or stabilization. Yes, Lee.
So is this theorem saying that is this theorem saying something like, if you take the category of quandles and you do a bunch of stuff to it and you stabilize it, then you get that? Or is it saying this is the correct, like, okay.
Yeah, so if I take the, right, what is the right thing to say? I take quandles, and then I don't know if I want to be cool, I say, animated quandles.
Oh my God.
And then I take the associated stabilization of this quasi-category, and that's okay. Modules. That's equivalent to modules over this thing. So Craig was telling jokes about racks earlier. There's also a version of this theorem for a rack, which is like a quandle, except you throw away the self-conjugation identity. There's a corresponding ring that goes on the other side. It's just, this is just some kind of, that the main ingredient is being able to analyze these homotopy types as you take bigger and bigger spheres for your powers, because those are parametrizing the kind of monadic part of the monadic adjunction.
Another question sort of related to this. So like, I see this category of modules and I think about like some sort of like K group with coefficient, like some twisted kind of K group or something. Is there like any interesting kind of quandle, like you could like take the stabilization of a quandle or something, and then you could sort of maybe consider some sort of twisted, like twisted K theory and look at K0 classes. Like, is that anything interesting, or am I just free associating?
That's a good question. I don't know the answer to that question. Yes.
So you mentioned a theorem of symmetry before and say like you get like quantum homology groups and they agree with like known things.
Yes.
Do you mean like you actually like you take like those like you take like the groups S quantles and the compute homology, like the group homology of them. Yeah, like they agree with like the classical group homology.
It doesn't agree with the classical group homology. So what people had done is they'd written down some recipe for taking a quandle and writing down like chains on that quandle with coefficients in a module that was some big chain complex with some boundary operator that was, it was a boundary operator, but it was designed to kind of mimic what was going on.
So it's like strictly like a new framework to compute like something that's like quantum homology. It's like a separate thing.
Yeah, absolutely. And in particular, like this recipe here is like, it's like a homogeneous or inhomogeneous chain. You write down the biggest possible chain complex that always works. But in some cases, there are smaller versions that work depending on exactly which thing you're feeding in. So that's kind of the utility of the Quillen homology type version of things, is that you can use smaller presentations.
In general, like if you take your group to be the quandle, like do the homologies agree, like the quantum homology and the group homology?
No, they don't. No, they don't agree. So the associated quandle, because the quandle, if I take a group and I forget the group structure, and then I take the quandle and then I produce the group back again, for example, that's not an idempotent operation. You get tons of extra garbage. It's so bad. So there's a little bit of a divide between how these behave.
I guess I was getting to like how to get those extra garbages. Just really helpful.
Yeah, absolutely.
Do we have any questions over Zoom?
Yeah, I have maybe like two questions. The first is, how do you define the higher quandles of a knot? Is it just like you take the higher homotopy groups of the like homotopy fiber of that map you wrote down?
I think that probably the right answer is that you don't kind of get higher quantles, but you get something like if I have a topological group, then the higher homotopy groups have some kind of stuff that's related to Samuelson product. So there's going to be some kind of algebraic structure, but it's not like I get a sequence of quantles all the way down.
Yeah, I was just, you wrote Q1, which made it seem like there should be like a QN for.
Was mostly being flippant.
My second question is, like, when you write homology theory for a quandle is like it's like a spectrum with a self-equivalence or something. This seems a lot like some kind of it seems related to filtered spectra, like it's a certain distinguished class of filtered spectra where all of the maps are like all of the structure maps are weak equivalences. Is there any like relation here?
I don't know. That's a fair question. I don't know. Sorry.
Any other question for Tyler here? Zoom? All right, let's thank Tyler again for interesting and sacrificing himself at the